Okay, let's see. I think it's about time to start. We were talking a little bit a second ago, but just for the sake of the video, there's a quiz online tonight. Let's check and see if it's appropriate, though. We may not have covered enough material. When I set up the course, I do reuse assignments from year to year. I don't reuse exams, but I use all the same homework and quizzes. It's all the same topic. I mean, you could cheat and figure out, get us a file from last year or whenever I taught it last, and you could turn in all the homework exactly right, but that wouldn't really help you much. So I trust that you don't do that, and that you study the homework, because that's where you really learn. I mean, I'm going through the same thing myself, right? I'm sitting in class myself, and I know that if I just copy down what he's written and I don't think about what he's done, and if I just go and I try to apply it without really understanding it, I'm not going to get anywhere. I have to really understand why everything works that he's doing. So anyway, I'm going through the same thing you guys are going through, and it's kind of funny in my class. He doesn't even bother collecting the homework. He says, "Look, you guys are adults now. You know how this works. If you don't do the homework, you're not going to succeed. So it's your choice." But I am faithfully going through and working all the homework, and it's kind of nice to know that I don't have to turn it in at any particular time, and I'm actually a little more motivated where I'm working ahead of it. All that to say, the philosophy is that the homework is where you really learn. So I've given you back your homework. All of you that attempted all the problems received full credit because you tried all the problems. And it's based, your grade is based on effort only. But what you need to do now, and I want to make this very clear, in all my classes I've moved this model, what you need to do now that you've received your homework back is go and look at the solution online, compare it to what you did, and see if what you did is correct or not. Let me make sure that the homework solution is available. Let's see, it is not, so I'll turn edit mode on. I don't know why it's on, and make it visible to you. So let's edit. Permit users to view content. There we go. So now you can see the solution to homework 2. So that's your next step, is to take your homework and look at it, compare it. Now let's see, the quiz. Let's find out if the quiz is appropriate, because I don't recall. I think it's quiz 1, chapter 1, quiz 2, chapter 2, and so on, but I'm not sure. Let's see. Closed piston cylinder device. How many people have looked at the quiz? Anyone? Okay. Did you feel like you knew how to do any of them or not? How to work any of them? A few? Yes? No? Okay. All right. So maybe we've caught up. If you get to this quiz tonight, I know some of you have not tried it. If you get to it tonight and you're banging your head against the wall and saying, "I have no idea," and this is something that we have not covered in class, let me know. We'll change the date. We collectively are in control of Blackboard. Blackboard is not in control of us. It's not a schedule that West Lafayette has passed it down and said passed down to us and said you have to do this by this time. I made all this. So anyway, let's see. Let's just get out of this. Now let me see, where were we in terms of examples and all that good stuff? It looks like that chapter 4 is the next example. The last one I worked for you was with a spring-loaded piston cylinder device. I have to apologize, though. I promised you guys I would create an assignment where you could get a little more detail on the project. I haven't done that yet. I will try and get that done tonight. In fact, I'm going to write a note for myself so I don't forget to do it, but I've got it written down on other lists. So. Like I said, there's a few resources that I've found that I think will help you guys, and hopefully next time we meet, I hope to go over to Bluegrass E-Cycle Wednesday and pick up the Fresnel lenses. So if you guys have not gotten into groups, oh, by the way, you guys, I let you self-select your groups, right? Just so that your schedules would match. Before you get done with this class, please come up here and jot down who all's in your group so that I can create the groups on Blackboard and assign the groups to the project. Okay. So please do that before you go. But without further ado, it looks like that we can go into the next set of presentations. Are there any? Oh, also homework. Any questions on the homework? There's another set coming up.
One of the very first problem I know has to do with
23 and 53.
That has to do with the program.
Oh, ease, that's right, yeah. And I had a couple people ask me to show you some things on ease. Okay, I'll do that. Ease is actually a really nice program. It's underrated in my opinion, and most people don't know about it. So, anyway, I have posted a demonstration version, and I'm working on getting the license for the full version because the people that make this software want it to be freely available to college students that are studying engineering. And that's a great idea because it's a really nice little program. But I've posted the demonstration version of it. The problem with the demonstration version is that you can't save, you can't copy, you can't cut, you can't paste. You know, they want you to have the license. But they want us to have a free copy of the license, so I'm working on that. Anyway, you can still work in ease. And I think that this program is going to be really beneficial for your project. And I'll show you why. If you look in the back of your book, go to the steam tables. And it doesn't matter. I guess let's go to the steam tables. Well, I say steam tables, so let's go to the steam tables for water. Well, it's the same thing. Let's go to the saturated tables for water, is what I'm really trying to say. And, well, let's go to page 915, so it'll be in metric units. Now, if you read the fine print down here, you'll notice it says source. Tables A4 through A8 are generated using the engineering equation solver software. So all this data, they generated from ease. And how did they do it in ease? Well, it turns out that in ease, let's see, there's it's about the third line. Issued by the International Association for the Properties of Water and Steam, IAPWS. Okay. So basically, a bunch of experiments have been performed to measure the properties of water and how water behaves with pressure, temperature, volume, all these things. And have been put into functional form. Now that functional form is a fairly complicated equation of state. Remember I showed you guys last time several equations of state that we're not going to use, but I wanted you to be aware of. Well, some complicated equation of state has been fit to the data, and then all they're doing here is printing the output of an equation. Okay? So where is that equation? Well, it's actually in the software, and we can use it. And I'm going to show you a secret. When you install ease, when you download it and install it, basically this area here is where you program. All of these are comments. None of these are any part of the program yet. But let me demonstrate something for you quickly. Right here, they've got a couple of equations set up. They've got x squared plus y cubed is 77. I'm sorry, I don't think I can make this any larger. Control plus only works in browsers, I think. So if you can't see it and you're on the back row, you're welcome to come up there for more space. And if you guys need to stand up and come here, that's fine. You can come up here and look at it. But x squared plus y cubed is 77. And then the square root of x squared divided by the quantity of 1 plus y to the 1/3 power in quantity equals 2. So this is highly nonlinear, two highly nonlinear equations. And if you'll notice, they've got an open bracket here and a closed bracket here, indicating that all this is common. Then they have a quote mark here and a quote mark here, which ease recognizes as a comment. Ease is essentially ignoring all this stuff because notice that there's either these open brackets around it or quotes. But then finally we get down here, this bracket ends this one, and this bracket begins another comment section. Okay? And so this is the end of this commented section. So if I try to run this program right now, ease will say, fine, nothing, no input, no output, right? So I can say, now here's the two most important buttons on here. Check equations, that's the check mark. And he says there are no equations, so everything's okay. And if we say run it, it runs it, but there's nothing to run because there's no code. Okay, this is all just comments, so it ignores it. Now I'm going to make this come outside of the comments so that these are declared as equations. And ease will solve these two equations for us like that and give us x and y. How would you solve this equation? It's a really tough equation, isn't it? You'd start by squaring this, but beyond that, you may kind of be stuck. Okay? Anyway, in fact, let's look at that just for the fun of it, to see what see what ease can do. Let's write it down. It's x squared plus y cubed is 77, and the next one is that the square root of x squared, and you'll notice they used when you get home and you look at this, you'll notice they've used an uppercase x and a lowercase x here. I don't think that will make any difference, but I don't remember, so we'll find out as we go. So that's over 1 plus y to the third equals 2. So how would you solve? Well, I would start by squaring both sides. X squared, right? X squared over 1 plus y to the 1/3 equals 4. I'd realize I've got an x squared here and an x squared here. I'd make the substitution, basically just multiply both sides by 1 plus y to the 1/3 power. That gets rid of the denominator. Now I've actually got x squared here, and I'm plugging in. So we've got 4 times 1 plus y. Let's make it a little more friendly. There's 4 plus 4y to the 1/3 plus y cubed equals 77. You realize you're screwed. Solve a third order equation. It's a nonlinear equation. How would you do that? How do you get y by itself? I don't know. Good question. That's where we go over and we start using computers and say we're engineers. We don't really care about the math and how you solve it. What we care about is getting the work done. So let's do it. Okay, now notice all that I've done is I eliminated a comma at the end. I was just saying that uncommon is. And I moved the end bracket here. And now when I hit the check equations button, Excel, or how did I keep saying Excel? Ease will tell us we've got 2 equations and 2 variables. There are no syntax errors. So it is happy with having an uppercase and a lowercase x. It must be recognizing that as the same thing. Right, so it's not case sensitive. Also notice that this section turned black, indicating that these are now part of the program, something that can be done. So we hit OK, we tell it to calculate, and it's done. We're finished. Okay. 2 equations in one block, elapsed time, minute, maximum residual, maximum variable change. What they're showing us there has to do with iteration, because what you do is solve an equation like this in a program, you guess and check. Okay. So there's some intelligent way of iterating to the solution. And it's telling you how much the variables change. In other words, the previous estimate of y might have been 4.054329, and it changed by something like the 6th decimal place. And so it's showing you how much the last change was. That's important to know that so that you know that your solution is valid. And so anyway, and then they tell you the maximum residuals, which is how much error is there in these numbers, or at least in the numbers that were estimated. So x is 3.221, y is 4.054. Nice. Let's find out if that solves both of these equations. So here's our question. They claim that x is 3.221. Here are your calculators, please. Squared divided by 1 plus y to the 3rd. Well, y is 4.054 to the 1/3 power. Now, if you're on your calculator and you're not sure how to raise it to this power, you can just have 0.333 and have a bunch of 3's there. Raise it to 0.3333333 power. Close enough. Let's check that one, and I don't care. I don't care who wants to do which one, but that's just one equation. We should also check this equation. This equation would be 3.221. I don't care who selects which equation, but I do want kind of a balance of the two. So then y is 4.054. We have to raise it to the 3rd power. The question is, does that come out to 77? Let's see if you can solve equations or not. Now, if you know how with a graphing calculator, you can do this on a graphing calculator. Usually, routines are built into the calculator to iterate and solve. Several different methods for solving this. This one works?
Square root of 1.
12.99969.
Yeah, it's a bunch of, it's pretty much.
We're engineers, that's right. Yeah, what about the first one? Anyone verify that one?
Yeah, it works out.
Works
It's
out.
like 77.00199.
Close enough, right? Okay, so this is pretty good. This is really nice. Now, that's not the only thing that ease can do. I sound like a salesman now. Okay, it's not the only thing that ease can do. It turns out that it's been a while since I've used these. There we go. It turns out that all this data you have in the back of your book is built into ease, which is really nice, because instead of having to do a bunch of interpolation on your homework, if you figure out how to use ease, you can have it do all the interpolation for everything. So you don't even have to work any interpolation. Not only that, I'll let you bring computers in here. So on an exam, if you think you will need to interpolate on the exam, just bring in ease. Tell me what your ease result, okay? I'd like to see your code. You can attach that to the exam, it's fine. Try to run this class in the most practical way I can, where you're really doing stuff more like you would in the real world. Well, anyway, let me show you a little secret here. Introduction to basics and concepts. That's not the one I want. I want something with properties of pure substances. There we go. Okay, properties of a pure substance. We hit OK. Now, coding in ease is pretty straightforward. I don't know a lot about ease. Fortunately, if you have some intuition about programming, you really don't have to know a lot about it. It's pretty easy to figure out. There's enough examples, and all I'm doing is hitting thermodynamics and a bunch of examples underneath. You can go and look and see what all they've done before. Now we can simply run the program as it is and see what it does. Let's just try it. Let's check the equations. Looks like it's okay. 17 equations, 17 variables. Tell it to solve. It tells us the fluid that it's using, in other words, the model that it's using, the model fluid, is steam, I8PWS, which we just found out what that is, right? That's the International Association for the Properties of Water and Steam. Let's change this because I maximized it. Over here we have all the results. Now what the heck are these results and what are they doing? Well, what they're doing is they start off and they declare which fluid model they want to use. This is a model of the properties of water based on a lot of measurements that are a lot more accurate than you and I could ever hope to do. Okay? So this is good research data. And that's the model. Now, dollar sign a lot of times, especially in basic, indicates that you're talking about a variable. So fluid dollar sign is the variable that they are setting to this model of steam, I8PWS. But there are other models. There's steam NBS. I don't remember what it stands for. I've looked it up before. It's just a different model for the properties of water. There's just steam and there's just water. There's all these different fluids you can set up. Those are not the only fluids. You can use R134A. I think they have ammonia built into this thing, if I remember right, which we don't have in our tables. Let's find out in just a second. Anyway, so set 1 is a set of variables. T, you could guess, would be temperature. Okay? And T1, T of 1, is 50C, 50 degrees Celsius. So it looks like that you have to put your units in brackets, and you better give it units. Now my guess is, if you wanted to put in 50 degrees Fahrenheit, you just put in F there. We'll find out in just a minute. V1, what do you think lowercase v stands for? Specific volume. That's right. In fact, you can look at the units and figure out what it is. It's cubic meters per kilogram. Specific volume is 4.16. P1, they didn't set P1 to any particular pressure. They said, let's set P1 to whatever the return is from this pressure function. Pressure here is a function with these brackets around it. You have to give it what fluid you're talking about, because you couldn't calculate the pressure or something if you don't know what model to use, right? So what fluid is it? It's this particular model. Okay. T, you have to tell it temperature and you have to tell it volume, and it will return pressure. Now think about it. This is really not that out of the ordinary for you. You're used to using PV equals MRT, and in this particular case, if we're talking about volume per unit of mass, it's really more like this, a specific volume, PV equals RT. The R is a property of whatever fluid you set, right? So notice they've told it the fluid is steam, so it knows what value to use for R. You give it two properties, temperature, specific volume, it can tell you pressure. Not only that, but instead of being the ideal gas law, which only works for gases, this model is good for the whole range, for compressed liquid water, for saturated water where you have a mixture of liquid and vapor, for superheated. I don't know how far it goes. They may not have gone very far into compressed liquid, I don't know. But the point is, this is a really easy way to get properties of water. There's probably a function in there called enthalpy. I don't know, let's find out. Just remind me of what I promised we'd find out and make this up as I go. Okay, what I'm going to do. Anyway, X is quality, and notice they have a function called quality. They give it the fluid, they give it the temperature, specific volume, it returns the quality. In fact, you can see the result right here. Set 1's results are here. Pressure, 12.35, temperature, 50 degrees Celsius, which we told it. Specific volume, 4.16, which we told it. Quality, 0.3459. What does that 35 roughly percent tell you?
Saturated liquid vapor.
right? And how much of it is in the vapor phase? 35%. Right, 35% of the mass is in the vapor phase. So we should be able to look this up in our tables, right? So go to your tables and find out. This is a saturated mixture, it's just water. So the tables where we were just a minute ago are where we need to be.
Can I ask you something while I'm thinking
Yes,
about
sir,
it?
please.
You substituted specific volume for volume, can you always do that? Like if you just have a
Well, I
specific
didn't-
volume?
No, I didn't substitute, I divided both sides by the
Yeah,
mass.
it's M or
And it
K.
became,
Oh, yeah. Okay,
Specific volume.
so if you don't have the mass, you can use a specific volume.
you need the mass in order to get specific volume. Good question.
I asked that because one of the homework questions about nitrogen, it gives you a pressure and a temperature, and that's it. And it says, find out this about it.
Well, use the ideal gas law.
We don't have to correct it for it unless it asks for it, right?
Well, you might check. I mean, all you really have to do is look up the compressibility factor for nitrogen and those properties. Essentially, the question is how close is the nitrogen to its critical property? No, it's probably pretty far away.
The question is just look up this, or calculate specific volume.
Right. Well, you need to know whether you need to correct
So
the
run through the whole
process.
process.
Well,
Okay.
what I would do, I would write down the critical pressure, critical temperature. I would go ahead and take the ratio. Did it give you pressure and temperature for the nitrogen?
Yeah.
I'd go ahead and calculate the reduced pressure and reduced temperature, which is just the ratio of the total pressure to the critical
Get
pressure.
Z, yeah.
Well, I wouldn't bother getting Z. I would see how close those two numbers were to one. If they're pretty far away from one, I wouldn't even bother looking up Z. I'd just say nitrogen commonly behaves as an ideal gas. It looks like it's doing the same thing. Does that make sense?
So
The safe way is to look up Z.
See, it didn't exactly turn out well.
Well, let's find out. Let's find out. We'll take a quick aside, then we'll go back to E. So what was the pressure in that problem, and what was the temperature?
The pressure is 300 kilopascals and the temperature is 227 degrees Celsius.
500 K.
Or 500.
27 degrees Celsius, and so how much in Kelvin?
500.
I'm sorry.
500.
500. Okay, did you look up critical pressure and temperature for nitrogen?
The critical pressure is 3.39 MPa. And the temperature, critical is 126.2.
I bet that we would have a compressibility factor Z that's pretty darn close to one, but let's check. All right, so the first thing I would do is I would calculate the reduced pressure and the reduced temperature. All you have to do that is take the ratio of the total temperature to the critical temperature. Total temperature is 500 Kelvin. Critical temperature is 126.2 Kelvin. The Kelvins go away. You get a non-dimensional ratio that's a little less than 5, probably about 4. The reduced pressure is the total pressure divided by the critical pressure. And that's 300 kilopascals. Don't you have to use consistent units? Divided by 3390 kilopascals. So this is going to be about 4, and this one's about 0.1 or so.
Wait, where'd the 500 Kelvin come from? I have 150 in my book.
I don't know, somebody said
T
it's
critical.
27 degrees. So
Temperature critical is 126.2, and then the temperature that
I
they
think
give you.
227 came from somewhere else.
what was the pressure in it?
Temperature is 150.
I have 227C.
Is this problem 3-98?
378.
3-73.
373,
That's
that's
problem.
Yep, it's 227 degrees Celsius.
We have too much in gas problems.
So one's about 4, the other's about 1. I can tell you already that you're going to have a compressibility factor pretty close to 1. Because at high temperatures and low pressures, gases behave ideal. This is a low pressure relative to critical. This is a high temperature relative to critical. Let's go ahead and complete it though, since we're already here. Let's look up the compressibility factor.
So, but the critical temperature is well over what I mean, this temperature.
The critical temperature is a property of the nitrogen.
Uh,
So it is what it is. The temperature that the nitrogen is actually at is well above its critical temperature.
But you can't treat it like an ideal gas, right?
You can, that's when you can. See, if you had ratios here close to 1, then you'd be in trouble. then you could not treat it as an ideal gas. Here, I'll prove it to you. Let's go back to the compressibility chart. You don't have the page number right off?
Yeah.
The right answer is yes, we have it bookmarked.
It's not there.
Ran out of bookmarks.
We have it bookmarked. That means you've been taking too many of my classes. I'll tell you where all the good stuff is in the book. Okay, 932. If we go to page 932 and we look up reduced temperature of 4, I don't have a large chart, I apologize, but the reduced temperature lines are the lines that kind of slope down to the right. Reduced pressure lines are on the x-axis, so we need to reduce pressure line 0.1. That's way over here on the upper chart. All right, see 0.1 on the x-axis? Page 932. So if we go up on 0.1, we need to find TR of 4. And there's a TR of 5 here at the top, so we're basically right at or above 1 for the compressibility factor, which means PV is about equal to RT. Does that make sense?
Yeah, but I'm still hanging up on this temperature critical and pressure critical. So if it's over that, if it's over what is listed as the critical pressure or temperature,
So that's not the way to ask the question.
Okay.
Are you talking about temperature or are you talking about pressure?
I don't really know what the hell I'm talking
All
about.
right, then that's what I suspected. So
What answer
let's
are
fix
you
it.
looking for?
I don't know when to count the gas, when I can treat gas as ideal gas and
All
when
right,
can I
here's
not.
the answer to your question. When TR is large and PR is small.
As
That's when it's up.
compared to what's listed in the book?
Well, you don't even have to say as compared to anything. This is a comparison because it's the ratio of pressure to critical pressure. That is a comparison. Does that make sense? It's kind of like did I get a good deal on my car? Okay, so let's say that you paid. Let's calculate the reduced price. Price sub reduced. Okay, how much? Let's say you paid $5,000 for a car, and you wouldn't look when you looked at the average price for that car, and you found that this was a $20,000 car. That's a pretty ideal situation, right? Okay. On the other hand, unfortunately, where this doesn't work is on reduced temperature. So I can't tell you the same thing as it's the other way around, because you want it to be as big as possible. So here you have to think about making money. I don't know why, but money analogies really work for me. I guess I'm just driven by money. I don't know. So here, if you're supposed to make, let's say that the going wage, whatever you're doing, let's say that you make, I don't know, $100 for a job that on average people are paid $10 to do, you come out ahead, right? So this one's like making money, this one's like spending money. The bigger this ratio is, what you've made by comparison to what you should have made. The smaller this one is, the amount that you pay by comparison to what you should have paid. Does that help at all? It's muddy the waters more. So you see how that ratio is a comparison between two things? It's basically, it just quantifies how close the gas is to its critical point.
PR over TR ends up being .02.
You don't want PR, you want P over PCR.
I'm talking, I've calculated TR to PR.
Okay, great.
And
So when they end up
PR over TR is .02.
why would you take PR over TR?
That's what you,
Pretty much you find your PR and you line it up with where your TR is, and wherever they have that is, that's your,
That's where you all
that's
see it.
that's where you gotta go to the table. to find
If it's
out.
close to one, don't worry.
Do it one divided by the other.
What's close to one? Yeah, see, it's close to one, don't worry about it.
Up the right chart.
I was just going by the example.
Well, in that example, they're probably taking the ratio of those two because they had to calculate the pseudo-reduced volume. Sometimes you don't have the temperature or you don't have the pressure. So you have to calculate the pseudo-reduced volume, but then you take the ratio of the critical temperature and critical pressure. What page are you on?
140. They have, on 139, the problem statement is that they have a refrigerant at 1 megapascal and 50 degrees Celsius. And it says to use the ideal gas equation of state.
Okay.
And then the generalized compressibility chart.
I don't see PR divided by TR anywhere.
Go to the next page.
I'm on page 140.
Now look in the gray box.
I am looking at the gray box.
It's not saying that it's being
There's no
divided.
PR divided by
It's
TR.
not saying anywhere that you're divided.
That's just two pieces of information, that's just two
Those
equations.
They probably want to go back and like, all right. well,
Right,
that's
exactly.
what
They took those two pieces of
And that's what you were
information.
talking about on the chart.
Right, now go to the chart that we were looking at. What was that chart number again, the page number for the chart?
Like driving nails and cutting.
932.
It's okay.
All right, I got it now.
You got it? Okay.
Yeah.
Anybody else? These are good questions.
That's a chart. What page was the chart on?
932.
932.
It's pretty simple.
If I'm gonna drive nails in concrete, I guess I better get a Hilti gun. Which, by the way, a Hilti gun actually works based on thermodynamics, so do
So
all
for
guns.
example, we just did an order.
Don't remind us.
Don't remind you. Everything is thermodynamics. Okay, well, let's continue. Does that help at all with the, do we need to say anything more about the gases?
Yeah.
Expressibility chart.
I'm still curious on how they got .7 here.
So it's going
In a different problem? Oh, we'll get to that in just a second. Let me finish off E's, because I've forgotten what all I promised you guys I would do. I wanted you to go to the saturated water table so that you could verify that E's has given us the right information. Which it should, right, because what's in your book is generated by E's. But just go and look it up for fun. But I guess we're desperate for fun in this class, right? If that's fun. So go look in the charts, what was it, 914, I think? Number sticks in my mind. Yeah, saturated water table. If we look up a temperature of 50 degrees Celsius, that's on page 914. The pressure is 12.352, which is exactly what we got here. So all it's doing is looking up or it's going to the equation that generated this very chart. If you look up the specific volume, 4.16, scroll over, there's some of the computer term. From 50 degrees Celsius, look at the two specific volume numbers that are listed. One is 0.001, the other one's 12. And where does this darn 4.16 come from? What the heck is that? It's right here. Well, there's only water, because water is a chemical, it's H2O. There's gaseous water and liquid water.
Yes, and there's.
You're right, there's a saturated mixture of the two.
There's going to be average.
Right. You let me finish. Okay. Is it the average? Yes, that's the average specific volume. Okay, so that's right, that's the volume per mass. And you can actually relate all these things together pretty easily. The quality is equal to the average specific volume less the specific volume of the liquid divided by the difference between the specific volume of the gas and the specific volume of the vapor. So if you were to plug in, the numbers we looked up for the gas was 12 point something, I think, and for the liquid was 0.201 something. Okay, if you were to plug all that in with 4.16 here, you would find that the quality is whatever it came out to, about 35%. Okay? Because all those things are related to each other. Basically what I'm saying here is that in a saturated mixture, there is not even one infinitesimal bit of mass that has this specific volume. There's none. There's only gas that has whatever specific volume was when we looked it up on that line for 50 degrees, and liquid that has the other specific volumes again. But with the right amounts of each of those, the total or the average specific volume comes out to 4.16. So all those things are related together. Fortunately, you don't have to worry about all that. You just plug it at ease and there you go. Now, the other two sets are other amounts of pressure, temperature, whatever. In this case, Set 2, they specify the pressure as 200 kilopascals. They specify the quality as 1. Now, quality of 1, what does that mean? It's all vapor. So all the mass is in the vapor phase, so it is a saturated vapor. Okay? And so you would expect that the volume that is returned here should be the specific volume of saturated vapor, V sub G. Let's look it up. Go, just flip one page over, because you're in the temperature table. Go to the pressure table, look up 200 kilopascals, and read off VG, and see if it isn't 0.885. So that's all it's doing. It's just, and here's what's so nice about this. Let's say I gave you a problem, and I wanted you to tell me these properties at 51 Celsius. Then what do you do? Because you got 50, and they go back one page. You got 50, and what's the next temperature? 55. So you have to do that darn thing called linear interpolation, right? That we, love so much. Right? It's not all that difficult, but it's certainly a lot easier to type 51 in there, hit solve, and let ease tell you the results. Notice the quality is a little bit higher. Specific volume and the temperature of the two that we clamped, we didn't have to interpolate at all. Which is really nice. The pressure also is a little bit higher, 12.98 instead of 4. Sorry?
I was looking down.
Oh, sure. Up here in the code, in the set.
In the function?
No, it's in the, where the tell what the temperature is. So that's where I typed it in. Well, 52 degrees, no problem. So interpolations, I think, are the fastest few C's. Set 2, I didn't change anything there, going back to that line, 200 kilopascals. Apparently the saturation temperature is 120.2, you can look that up. We already looked up the specific volume of saturated vapor, and then the quality is 1, we told you. Set 3, there's two different things given, a temperature and a pressure, and there's a function here called volume that's been used before, where you calculate, or you let it calculate the specific volume of the whatever it is. Now, we don't know if this is in the saturation region, superheated region, or what. So go to your saturated tables and we'll figure it out. Why don't we go to the temperature table, which I think is where I left you, and look up 250 degrees Celsius. Now, 250 degrees Celsius, what would the pressure have to be for us to have a mixture of vapor and liquid? 3976.2.
3976.2. That would be below that.
That's right. But our pressure is 400 kilopascals. All right. So we have to have so do we have to have less or more pressure to be safe for water? Well, what was the pressure you read off? I'm sorry.
3,976.
Okay. So we're at a lot lower pressure than that. What would that suggest to you? Vapor. That's right. Because when you reduce the pressure on something, it tends to boil off. So the way that ease tells you that is we've asked it to compute the quality of the fluid, but since it's not even close to being saturated, quality doesn't actually make any sense. So what ease returns is positive 100. That positive 100 indicates that quality doesn't make any sense, but we are above quality. Okay? We're in the superheated region. Similarly, you give it two other temperatures and pressures. If you compare this to your book, you'll see that we should be below saturation. In fact, quality returns negative 100, indicating that it's subcooled. I'm sorry?
Super compressed.
I just call it compressed. Or it's called super compressed. Superheated, I guess, just sounds fun. I don't know why we do that.
They match up on the superheated.
Sorry?
For set 3, it matches up on the superheated.
Yeah, sure. You could probably go to the superheated tables and look that up. And get that all.
So how do we change it to the refrigerants and the ammonia?
Good question. Let's find out. Now, I'm not an ease expert by any stretch of the imagination. If you guys end up using it for your project, you'll know more about it than I do. Fortunately, it is actually very easy to use. That's the name, okay? So, watch this. I'm going to take a guess. R134A. That's a refrigerant. Check the equations. It seems okay. Calculate. Temperature's out of range. Basically what it's saying is that we don't have data at the temperature you asked for. The allowable range is between 170 roughly Kelvin and 460. And I think they're indicating this one because the temperature I specified was 250 Celsius. So 250 plus 273, yeah, that's more than 460. Okay, so there's the problem. So I could simply comment out that set. Notice I was using this just for water. So it didn't give me a result yet because it doesn't have data in this range. So I'm gonna make this easy. I'm just going to put brackets around it so that ease will ignore it. Check my equations, no problems. That window back down. Calculate, there we go. So set 3 is blank because I got rid of it. Okay, but here's the data for R134A. It worked, it recognized. Now let's try something else. That was a lucky guess. What if I had chosen R-134A? Or what if I made this a capital letter instead of a lowercase letter? So caps lock. Let's see exactly how forgiving ease is. It doesn't recognize R-134A. Okay. Let's try lowercase r. Doesn't like it. So maybe it doesn't like the dash. Let's try a capital R without the dash. And it likes it. So it's just not case sensitive, but it couldn't deal with the dash. Now you're probably more interested in something like ammonia.
Bonus points if you spell it right.
I'm sorry?
Bonus points if you spell it right.
We'll find out. Bonus points achieved, thank you. Level unlocked. Okay.
What if you put NH3 or whatever?
NH3? I don't know, let's find out. We've already figured out it's not case sensitive. It doesn't like NH3. Now there's probably a help somewhere that lists all the fluids that are available. I don't know, I haven't looked. Can't get help from this problem. This program is too old. You'd have to install a package that lets Windows view old help files. It's not
So
easy.
where it says set 1 and typing below it, was that just there?
Yeah, that was just there. I went to thermodynamics, properties of pure substances, and selected the first one, properties of a pure substance, and hit OK. And this is what I found.
And that was under
Thermodynamics, properties
Thermodynamics.
of pure substance.
a big word, all the way to the right.
Yep, the one at the end.
Can you, save your own techniques?
I cannot save any of this because this is the demonstration version.
Now what about this version, right here?
I think that's the demo version also, but I'm not sure. I don't think you can. I've asked Greg to let me know if we have ease licenses or not. And I'm going to try and, what I really want to do is find the full install file and just post it on Blackboard if you guys are downloading these. Because it's,
If they wanted it to be free, why don't they just open source it?
well, they want to sell it to companies, but they want students to use it. So the students will, when they go to companies, will ask to buy it. That's what they want. It's not free except for to
It's not
education.
that, let's share our information with the world, it's, let's get these kids hooked on it early in life so that they're sprung.
Yeah, fix all of them.
You got it.
Like
Capitalism.
For heroin.
Start them early.
What's that?
Start them early.
It's a big job,
That's right.
but
Get them addicted and
Sorry.
then be the dealer.
So much is licensed out.
I don't know.
Probably, I don't know if
that's
that's
it's free, and you wanna know the other
For you,
problems.
it's free because you're a student.
Yeah.
Okay, so anyway, I know that I've gone through this before, and every semester it comes around, I forget to ask for ease to be installed. That's my fault.
It wouldn't get done if you asked for it, nothing else does. So, don't worry about it.
I won't make any comments on that. Greg does a lot of good things for us. I appreciate it.
Well, I could be a really good worker too, but if you asked me to dig a mine by myself,
That is true. There's a lot of work to be done. Okay, now here's the secret. All the problems I give you guys are essentially already in ease. All you gotta do is open it up, tweak the program, and away you go. In fact, I think the problem number was even 23, wasn't it? So that's the very program you need to use. You just have to tweak it a little bit to get everything out of it. Okay? So it's not all that difficult to use this for this homework. So. Any more questions on ease or homework or anything?
could you, I don't want you to hand me the answer to 78,
Okay.
but I couldn't really get it started. I didn't
Okay.
see-
78, how do we get started? I don't know, let me find out what 78 is asking.
It's just an equilibrium question. Got a couple of tanks,
It's an equilibrium question, but how do you work it when I'm off balance? How do I work an equilibrium? I use bad jokes because you'll either laugh with me or at me. At least I laugh. Okay, the two-tank problem. Well, what really confuses students about this is they're not thinking about states. There's our valve, and here's the two tanks.
I know the temperature in state 2 is 20 degrees C.
Okay? So
That's and I mean, it gives you your individual temperature of the tanks before they're allowed to get the equilibrium.
Okay. Now, for some reason, I guess it's a human factors thing, I don't know. It seems that students get confused about the fact that there's two tanks and there's two states. Let me draw the second state. It looks exactly like the first state, except that in state 2, everything is at equilibrium without the valve essentially being there. Basically, the valve has been opened. Make more sense now? So this is state 2. This is state 1, bless you. And really, this bit of information here goes with state 2. So let me ask you a question. What's the temperature in the right tank in state 2? What's the left tank? Now in state 1, what's the temperature of the left side?
25 degrees C.
How about the right side?
35 degrees C.
Try R, 35 degrees C, okay? So 25 and 35. Basically, you have two independent systems that make up state 1. So what else do they give you? Do they give you pressures?
They give you the volume of the left tank,
Okay, V equals how much?
1 cubic meter.
Okay, anything else?
They give you 500 kPa.
500 and what? Oh, kPa, 500 kPa.
Yes.
Is up the left one and 200 on the right one.
And it's 5 kilograms
Up there.
On the right?
on the right one.
Okay, anything else? No, that's all you need. All right, well, what they're doing here is they're trying to point out that PV equals MRT is only good for one set of mass that has the same properties. You can't apply this to this whole system. Won't work. You got two different pressures. You can't plug in two pressures here. You can't take some average. That doesn't work. So what should you do? We should try to find everything else. For example, how much mass is in this tank? And how much volume is in this tank? Well, if you apply the ideal gas law to this side first, you can answer the question because the mass there is simply PV over RT. You've got PV and T for the left-hand side. You can look up R for the air, which is what's in here, right? And you can do the same thing over here, but this time, PV equals MRT will rearrange to V equals MRT over P. So you use two ideal gas laws. Once you're done, you will know how much total volume there is. Let's say V left plus V right. One of them was given to you, the other you can find. And you'll know how much mass there is from the left tank and from
And
the
you
right.
just plug in PV.
Then you plug in PV if you want to on the right hand or on state 2.
Okay. Okay.
Good
It's
questions.
a lot simpler than the way, just looking, trying to look at it as a whole, when you break it apart like that, makes it a lot simpler.
Right, well, you can't analyze it as a whole in state 1 because you have two different pressures, two different temperatures, everything's different.
Just wanted that kick in the ass.
No problem. You just, it's not that, you just needed a jump start, that's all.
No, you can't say that.
Same
What's that?
difference.
You can't say that.
Yeah, you can. So the answer is that the DVD that comes with your book is more junk. Is that a surprise?
Can you demonstrate how kilojoules equals kilopascals times kilograms?
Times cubic meters?
Cubic meters.
Sure.
They have it,
Just to prove.
The question was, kilojoules, how do you convert that to something else? Well, let's find out. Our ultimate goal is to get to kilopascals times cubic meters, because I know that's the answer. But if you don't know the answer, what do you do? Well, what is a kilojoule? Well, there's a kilo, let me just set the 1,000 off to the side so I can put the joules. is a Newton meter, right? A Newton, on the other hand, is a kilogram times a meter per second squared, and then I have this meters multiplied by it. Now, if I'd like to get newtons out of this, I probably shouldn't, I'm sorry, if I want to get kilopascals, I probably shouldn't go this way. Let me try something else. Because I remember that a newton is related to Pascal by cubic meter, basically, right? So if I take a newton per meter squared, I'd have pascals. So I can just add in, let me do it this way, so that it's clear. A meter squared over meter squared is just one. Right? So here's my meter squared over meter squared, and I still have the same thing. Bless you. This is just Pascal. Bless you again. So Pascal times a meter squared times a meter is the same thing as a kilopascal times c cubed. Okay. Anything else? All right. Well, then let me jump into my slides. I believe we're on chapter 4 because we finished off chapter 3, but I'm going to open chapter 3 just to make sure.
Any projections on when the next little mini exam is gonna be?
Well, it depends on how much we're covering. We should be able to have one next class, because essentially the quizam I gave you from last time was over chapter 2, although I didn't really intend for it to be, but it is. You guys handed in homework. In fact, I've handed back the homework for chapter 2, so I should be able to give you a mini exam over chapter 2. So that will happen next class. Assuming I remember to write it out. I'll come in here to class and you guys will know I've forgotten if I don't have a stack of papers for you. Okay. Last time a couple of students came to my office and asked about it and reminded me, I said, oh, I better write something then. You're right, I need to give it. I had forgotten. And one of the students said, why did you remind me? So, anyway. Okay, have we talked about boundary work yet in this class? I don't think we have. Chapter 4 talks about boundary work. Now, we are very, very interested in moving boundary work. Why? Because it turns out that many of the machines we use rely on moving boundary work to do it. Okay, either a fluid, well, always we're interested in a fluid doing work and making something move. Plenty of camera shake. It's okay. So it's just for one student. I'm going to post that. And when you go out of town, I'll do the same thing. Okay, so anyway, moving boundary work. The idea here is if you have a gas under pressure and you allow that gas to expand slowly, you can have that gas do work. In fact, let me show you a kind of humorous video. I don't remember if I posted it for you guys or if I just put it into the 220 class. Let me look and see. Yeah, I just put it in the 220 class. That's okay. We can find it. There we go. V6 working paper model. Have you guys seen this? It's not going to do anything real practical, but it's cute and interesting. Some guy has too much time on his hand. He made a paper model of an engine. It actually works. I think he's used a lot of super glue to stiffen up the paper. So notice the edges of the paper look wet, but that's the way they look when you use super glue on it. I guess some engineer was sitting at his desk bored for too long one day. So not only has it built a replica of an engine, he's built some type of motor, pneumatic motor, to spin the engine based on a balloon. Now that's pretty useless. Fun. Okay. At the end, he just squeezes the balloon and gets the rest of it out. But anyway, the reason I showed you that is because he built, well, because it's cool, but also because he basically built a motor that ran off of air. So the air had to push boundaries to make the shaft turn, which then made the engine turn. And so it wasn't the normal way where the engine was actually driving something. It wasn't actually running air through the engine itself to turn anything. And the air was going through a pneumatic motor, basically, to turn the engine. Anyway, so we're always interested, so they didn't show us that part, right? So he didn't have valves or anything in the engine. That would have been really complicated. He just had an engine with pistons. Anyway, so we're interested in allowing pressurized gas pardon me, to do work by pushing a piston. Let's get through this slide and then you can have your break. So we've got a pressurized gas here. We call that our system. And we're going to allow the gas to expand the piston and, well, expand the volume of the system by an amount ds, or it's going to move the piston by an amount ds, expanding the system. Now the piston has a cross-sectional area A, and there's a pressure of the gas. Now, the gas is going to expand, applying force, doing work against some external load. So the amount of work that will be done is just F times ds, because remember, work is force times distance. So if we were to integrate and add up all the small amounts of work in moving the piston from state 1 to state 2, then we have to write it this way. It's just the integral of that force over distance. Okay? Now, it's not really a surprise that we would need to integrate this, because if you think about it, as this piston allows the volume to expand, or as the gas pushes the piston out, the pressure in the system is going to drop. So we actually can't just say initial pressure, final pressure. We have to add up the force of the pressure over the entire process from state 1 to state 2. But you can see we're just plugging in force and differential change in distance and basically just adding them all up. That's what integration does. It adds up a bunch of things that go to zero to find what the limit is. That's integration. Now, if you look at the piston, if you think about it, the force is equal to pressure times area. So we can plug that in and make the substitution for force, just pressure times area. But then if you think about it a little further, you might realize that when the piston moves from state 1 to this infinitesimal distance ds, the system will increase volume by A times ds. So this A times ds really represents a differential change in the volume of the system. So we can make that substitution and say that boundary work is the integral of pressure times differential volume changes, or added up between two states, okay, along the process. All that's nice. If you remember it, great. Here's what you need, and you don't even need this exactly. You need the integrated forms of this equation. Now, in this class, I will make you integrate this once at least on a homework. Okay? But most of the time, you will need the integrated forms. So I promised you have your break. Let me just get through this real quick because this one follows tonight. So if you look at what's going on here, all we're really doing is saying, let's turn this piston on its side, go from state 1 to state 2, and look at what's happening. Well, the pressure is decreasing the whole time, which is what we expect. We don't know exactly what that looks like, but just for now, let's pretend that's the shape of it. As you move the piston along the process path from state 1 to state 2, we're going to reach a point where we go from a volume here to a volume here. We let that be a very small distance, and that is a differential change in the volume of the system, where this is the total volume of the system. Okay? Now, during that time, what will happen is there will be an average pressure, right, from here to here. That average pressure times the change in volume represents a differential amount of boundary work that is done from here to here. Now, when you add up, or in other words, integrate from state 1 to state 2, you add up all those small amounts of boundary work, and that would be the total boundary work generated by the piston going from state 1 to state 2. And so in other words, the area under the process curve on a PV diagram represents boundary work done by the system. Questions so far? At this point, your eyes are all glazed over. You're just waiting for the break, right? Now, depending on the shape of this path, the amount of area underneath it will vary. There might be a process path that gets us from the exact same initial state to the exact same final state, where the two process paths are different and have a different amount of work underneath. In fact, the higher up that curve is, the more work is underneath. Now, does this have any practical application? Well, you got here today by what method? Did you run? Did you walk? Ride a horse? You drove a car, right? That car has an engine in it. We still haven't figured out electric cars all that well. We haven't figured out how to make them real economic, right? And when we do, I'm going to buy an electric car because I can get a much lower price per mile because the electricity company will sell me power at a much lower price than Shell Oil will. Okay? I'd rather have an electric car, honestly. They accelerate like crazy. It'd be a lot of fun to drive, but they're too expensive and batteries don't last, as far as I know. I can't afford one, so I'll stick with what I've got. But, so what got you here today is an internal combustion engine. Well, what happened is, during the power stroke, the cylinder follows the process path, moving from top dead center essentially to bottom dead center, and does force over distance, right? In other words, the pressure of the gas causes the cylinder to expand, the piston moves down, and the work that is represented by the area is higher than the amount of work required when the crankshaft pushes the piston back up to compress the gasoline and air mixture. Does that make sense? There's a decent amount of work required to do this. To take the gasoline and air that is not burned yet and compress it in the cylinder. It takes quite a bit of work. You have to apply a decent amount of force times distance. That's why in your car you've got multiple cylinders. Why didn't they just give you one big cylinder? You ever wonder that? Why not one big cylinder with a long stroke? You can make an engine that's nice and not such a block, right? And you could possibly fit it nicer in the car somewhere. Why not a long cylinder? Well, the reason for it is that if you had just one cylinder, it'd be very rough power, right? You'd have to have a big flywheel to smooth it out, because you have to somehow recompress that piston along with the process path so that it can expand again and you can keep going down the road. So multiple cylinders make the engine run smoother. So anyway, also there are other reasons, but that's a simple thing. So anyway, just depending on exactly what the process path is, you notice when we're moving from state 2 to state 1, we're moving in a clockwise direction. Clockwise processes on a PV diagram generate boundary work. They have boundary work coming out of them. I'm sorry, I said that wrong. I said processes. Notice in this cycle, we're moving in a clockwise cycle. So what happens is these clockwise, any clockwise cycle on the PV diagram where your axes are oriented normally, like this, positive to the right, positive up. Any clockwise cycle is generated in that amount of work. Okay? The counterclockwise cycle is consuming work. Okay? So anyway, the net amount of work we get out is just the difference between the work from process path A and process path C. If process path A has an area of 10 kilojoules underneath it, and process path C has an area of 5 kilojoules underneath it, then the difference between those two is just 5 kilojoules. That's the amount of work we would get out of running this cycle. Okay? All right, why don't you guys take a break, come back. And when you come back, we will talk about special types of processes where we can actually calculate the boundary work.